I think I'm just going to take you to some simulation. I think that may be the the sort of straightforward because this is something that you probably cannot see by eyes. So that's why the simulation might help. All right, so you guys can sort of type along if you like. So you can go to just open up a web browser, and then you can go to, once again, we're going to use the same place like we saw before. This is still on here. So we're going to go to PHET. All right, you just do the search on that one. All right, and that will take you to the same place. All right, there's so many interesting simulation that you can try. And then we're gonna go into physics area. And all right, let's wait a bit. Okay, so what we are going to focus on is now is the electricity, magnets, and circuit. So I'm just gonna uncheck all those and just gonna focus on just the electricity stuff. All right, and the one that I would like to take a look at first, all right, is just the first one, the upper left corner. All right, let's start with that one. Okay, it's an HTML5, so you guys can just run on the web browser. That's kind of nice. Okay. All right, just wait a bit. Okay, and this is the scenario that you probably have experienced. Some of you guys probably get some static shock from time to time. All right, or sometimes it doesn't have to be a shock. It may be just an electrostatic attraction or something like that. So in general, what we are talking about is for all of the objects around us, there will be charges already built in because that's the fundamental building block of all of the materials. It's based on atoms and everything. So the atoms, now we already know there's a nucleus in at the center, and the electron is sort of orbiting around. And when you look into like a bigger picture, there will be like bunch of those. However, because now we know that the electrons are actually easily moved because it's so, I was it's so light and it's so small. We don't even know the size of it, and it seems like electrons can actually wandering around. So that's why every time that you have some sort of like a contact, or just pure contact might not do anything much. However, there will be some material that sort of like easily sort of like can give off charge easier than other type of material. For example, in this one, like if you're wearing a sweater, for example, and in this simulation there is a balloon which made of maybe rubber or some polymer, and then this simulation try to show you that if I sort of like bring this thing close, then the balloon can pick up some electrons from the sweater that's sort of like easy to remove from the sweater. So that's why in this case, after you take the balloons and make into contact with the sweater, the balloon can pick up a little bit of some extra charges, which is in this case is the electrons. All right. And from the history, we name that type of charge to be negative one. Okay, that's naming thing. And then we take the rest to be positive one. So that's why every time you talk about electrons, we're gonna say that the electrons comes with the negative charge. Okay. So what you can think of it is at this moment is now the balloon has some extra negative charge in itself, and now we know it's from electrons. And then when you sort of like try to bring this thing out, you can take a look at the sweater now because it lost some of the electrons. So the sweater itself overall will be a little bit more positive because it's already lose some negative stuff. So if you try to sort of like separate the balloon out and then you let it go, it's gonna sort of like move backward. It's like something's try to sort of bring them closer again, and that's we're gonna call them electric force. Okay, so this is some sort of like the the simulation that showcased that charges can interact with each other. So that's why we're gonna sort of like somehow try to calculate the magnitude or maybe directions of these attractive forces, something like this. All right. And the force that originated from different kind of charges, we're gonna call them electric force. All right. And this is the thing that also happens if you bring this balloon next to some maybe paper, wall, or whatever. Now you can guess what is going to happen is the balloon is seems to like stuck on the wall or on some surfaces, and that's because the balloon has some extra negative charge in there. And on the wall over here, I mean, normal situation that will have the same amount of positive and negative charge on it because it's neutral. However, when you bring the balloon closer, this is what happening inside. If you focus on the movement of the charges inside the wall, you can see that the electron seems to get pushed away deeper into the wall a little bit. Okay. So sort of this is something that I want to sort of, well, just tell you right away that when you have the same type of charge, in this case, negative and negative. So negative and negative will push apart. So this means the interaction between the same type of charge will be the repulsive force. Okay. And by this effect, the electrons get pushed deeper into the wall. So overall, on the surface, the net charge seems to be positive because the electron pretty much get pushed deeper into the surface. So that's why the balloon comes with a purely sort of like a net negative charge. So that's why when you bring it closer to the wall, it will feel that the wall has a positive charge waiting for it. So this gives you another conclusion that the different type of charge will have an attractive force. So in this case, positive and negative. Negative from the balloon, positive from the wall, and that's it. So that's pretty much give you the sort of like the whole idea of electric field. I'm sorry, the electric force comes from charged particle. Any particles that has charge in it can interact through electric force. Is that sort of like okay? I think without this kind of simulation or the scenario, I would say that I don't know how to make things a little bit more physical or a little bit closer to reality. If I just introduce to you like, hey guys, there is two types of charges, and then okay, you guys accept that, of course, positive and negative. But this is more like something that you can see a little bit easier because you see static charges well a lot of time. um Actually there's so many situations that you can feel if you use like food wrap, the plastic, the food wrapping thing. Then every time that you bring out the plastic wrap, then you feel like it's sort of like try to stuck in your hand or something like that, right? It doesn't seem to float in the air very like independently. It seems like it will stuck in here, and then we try to wrap onto the container, the food container. It seems like it's stuck on the food container as well, something like that. So that kind of situation was due to this electrostatic force, something like this. And every time that you try to pull something apart from that plastic wrap, so it's a plastic on plastic, and then when you try to pull them apart, there is some sort of like some changes in the amount of net charge on that plastic wrap. So that's why it has a net charge on it. So every time that this plastic wrap try to get onto some surfaces, it seems to stuck on it. Something like it's the same as like the balloon that when they bring it closer to the surface of the wall, it seems like to stuck on it. Same thing. All right. So this showcase the electrostatic force and the charge that responsible for that force. Okay. However, in our class, we're going to go deeper in the sense that we probably going to look at each charge individually, and then we're going to have like a group of charges and then try to calculate the net force due to those charges. So we're not going to sort of do like a collective, like we're not going to try to calculate what is going to be the net force acting on the balloon or something like that. That would be like a macroscopic picture that we're not going to do. We're going to look at charge like one by one and try to understand what is the behavior of the electric force, the behavior of something that we're going to define later, electric field, electric potential, on and on. And that will be the fundamental of everything else that's going to come later. Okay, but this gives you an overview of what is supposed to happens to charges. Okay, all right, so in conclusion, you have two types of charge by just look at the sign of the charge. So you have positive and negative. That's it. Okay, and that's fundamental down to the particle. And the particle that you're probably most familiar with is electron. That's negative. Neutron, well, if you remember that, that's neutral. So it's zero. So that is no charge. And you have proton that is positive, something like this. All right. So those are sort of like this property of charge is intrinsic and so fundamental that it's stuck into the fundamental particles. So some particle can have negatively charged, some of them can be positively charged, or some of them is neutral. All right, so that's sort of like another property of particles in this universe. Okay, apart from mass, of course. Right, so we learn about mechanics and all this stuff using mass, and now we're going to turn our attention to the charge. That is another side of the property of this universe. All right, is that sort of all right introduction? All right, I hope it works. Okay, all right, that's that, and then let's come back to the part that we are trying to get to. So that's the starting point of today's lecture. We're going to learn the electric property of material or of particles. All right, and the things that are responsible for that is charge. So we're going to learn what is the effect of the charge around it. We already saw that there are some interaction between them, and it can exert some force. So we're going to name those electric force. However, we're going to describe the force through electric field. So actually, these two concepts of the force and the field, eventually, to me, they are going to be the same for the purpose of this lecture. All right. And then I'm going to explain my logic of studying this topic a little bit. All right, it's coming. All right. And the conclusion that we get from this is the Coulomb's law. That is another law that is pretty much as big as Newton's law. Okay. Newton's law is good for mechanics. The Coulomb's law is the fundamental and is good for electrostatic charges. So that's pretty big. Okay. All right. So I'm going to try to go slowly today because, all right, from the experience, many students had some problems with this starting point of the electric topic because today we need vector again. Okay. All right. So that's what we are trying to get to is we're going to come back to manipulate vectors again. When I say again, mean you have done this in forces. When you do Newton's law, you have to do like component of forces and all the stuff. And it seems like it's been a while because we do some thermodynamics and other stuff. We don't have any vectors much anymore. And now we come back to this. We're going to need it actually. That's something that we needed. So that's with the whole topic today. That is the vectors manipulation. Okay. So this electric stuff, all right, starting with the charges that I introduced to you, lead to electricity and all of those phenomena related to electricity or the stuff. And eventually, toward the end of the course, it's going to lead you to magnetism as well. So that's why, in general, this electricity and magnetism usually comes hand in hand. So that's why it's a big topic in physics. Okay. And this is the electrostatic that we talked about. So you can comb your hair, for example. That would be some sort of like a contact and some frictions going on, and then there will be some charge transfer between your hair and the comb, and then the comb gets some extra charge. Then you bring it closer to some surfaces. Then you have electrostatic attractive force, something like this. Okay, so this is probably something that you have already tried or sort of like did some experiments back in like when you were young and all this stuff. Okay, so we already saw it that are positive and negative charge in here. Another thing that I just want to sort of like, just let you know and just give you some observation and like, hey, have you seen this or something like this? It turns out the charge that we classify as a positive and negative, it turns out to be quantized. I don't know, have you heard of this word or not? But you probably have heard of some like quantum physics, thing like that. Okay. But the quantized, quantum, quanta, whatever, these words are trying to say that the nature has something that is discrete. Discrete means come in steps. Okay. What does it mean? It means you might say about Ajahn, can I have some charge with this much of charge? You probably can say like, hey, I can have any size of the charge that you like. Okay, you can have like 1, 2, 3 unit of charge, but it turns out our nature say no, you cannot. You can have only numbers of charge available in this universe, and it turns out those charges, those available numbers, are multiple of this number. And this number is something that's going to stuck with you for a long, long time, especially for those of you that do communication, electronics, some, computer simulation. I mean, computer, of course. But even though if you do hardware or something like that, you have to deal with electrons. And it turns out the charge of the electrons that we said is negative charge has the unit of charge built into the electron. This is the magnitude of that charge. 1.602 times 10 to the negative 19. And we name the unit of the charge to be Coulomb. All right, that's the unit of the charge, the amount of charge in an object or in a particle. So what you have over here is, it means it looks like the charge of the electron, which is, now we know electron is quite fundamental already, all right? It seems to be the lowest amount of charge that you can get. Not only the lowest, it's pretty much like a fundamental unit, a block, like a block, one block of unit of charge. So this means in this universe, you're not going to find 1.7 times 10 to the negative 19 Coulomb charge. That's not available here. Here, I mean, this universe doesn't exist. If you say, hey, Dan, can I turn into like 1.71? Nope. 1.72? Nope. 1.61? Nope. 1.59? Nope. I mean, times 10 to negative 19. No. This universe, all of the charges that we will be talking about in general, not in general, is like, well, when we're talking about, it's going to be multiple of these numbers all the time. But the reason that we don't care much, because this number is super, super, super small, is negative 19 in power. So if I say 1 Coulomb, that will be fine. Right? You pretty much can come up with the amount of electrons that you want to sort of, collect, and then give the net charge of 1 Coulomb. You can do that. All right. But if you dig down into like the fine unit, like super, all of the digits in that, it might not be exactly perfectly 1 Coulomb. Well, it just, it must be multiple of this. And then we usually use the E to be like a constant representing the electric charge, the charge of an electron. Okay, sounds okay, guys? I know its introduction may be a little bit long, but I hope this seems to give you an overview. So what I'm saying is the charge of 1 electron is quite small. But of course, when you say small, it's small in our everyday life. But if you're doing like think about like what is going on inside like a CPU, the chip and all the stuff, the Intel, the AMD or stuff. Now this is not small anymore because now you're going through like 5 nanometer technology that you try to do the chip and all the stuff. So now number of electron is going to be quite low in there, and then you talk about bunch of electrons that's not as big as what we are looking at around us right now. But if for us like we are talking right now, if you talk about 1 coulomb, it takes that much of the electron to gather around to give you 1 coulomb. So that's like million. So that's a lot of electrons. Okay, so that's why there's no doubt from time to time you might just have to look at like, some super small units of Coulomb, like maybe millicoulomb, microcoulomb, nanocoulomb, because 1 coulomb is huge. Okay, sounds good. All right, so this E is representing a number, and this number is the size of the charge on an electron. But just to be clear, because electron has a negative charge, so every time you look at an electron, you might have to say that it has a charge negative E, because E is just a number. Think of it that way. And if you have a proton, that is another kind of charge, which is positive. It turns out it has a positive E charge. Okay, you guys with me? Okay, so the E is representing a number. And then you just add the sign to indicate, is it going to be a negative charge or is it going to be a positive charge? Then you can just add the negative and positive sign in front of the E. So like this one. Okay, electron is a negative E charge and proton has a positive E in it. So this saves you sometimes if you don't want to write like 1.6 times 10 to the negative 19 all the time. You can just use E for that. And okay, just add on top of this neutron, that's 0. There's no charge on it. Okay, sounds good. All right, keep going. Okay, and this is it's a textbook introduction to the force acting between charges. And conclusion that we saw from the simulation was, if you have the same type of charge, it's going to exert the repulsive force. So they're going to repel each other. Okay. On the other hand, if you have opposite types of charge, positive and negative, it will be an attractive force. Okay. But one thing that you can notice right away, because according to Newton's third law, these force will be action and reaction. So it means they're going to repel each other. So that's why there's no doubt in this figure, it's the same magnitude of force. They're both F. But of course, it's going to point in the opposite direction and it's going to acting on the different objects. Okay. But in terms of the sizing of the force, they are going to be the same. Okay. Same thing with this attractive force. Okay. They're going to attract each other. So the magnitude of the force will be the same, pointing in the opposite direction and acting on the opposite objects. Okay. Sounds cool. All right. So that's good. Positive, negative. All right. And if you try to classify the material into categories that based on how good the material can conduct, okay, that is another word of something electric. To conduct means how well that material allows the charged particle to travel. And actually, I can be more specific. Mostly electrons, because electron usually the particles that actually move, right? And the nucleus is so big and all this stuff, so usually it doesn't move. So if we try to classify the materials based on how well the electrons can travel in that material, you can classify them into 3 types. The first one, of course, the name implies, conductor. So electric charge can move quite freely. So that's good. It's easily moved inside. And that lead you to something like metal, silver, gold, copper, steel, seawater. Okay. So even though I said most of the stuff that you deal with are electrons that moving, but this is a good example that the seawater, it turns out to be the ion. Okay. So there is a possibility of when you have like positive charge or negative charge, that's not in the fundamental particle like electrons. It could be like ion stuff in here, like for example, sodium and chlorine, something like that. So what you have over here is usually that's what usually it's going to happen is the ion itself can actually travel, and because this is inside the water, so it's good. So this is a good conductor. It can conduct electricity quite well. Okay. On the other hand, you could have like an insulator, the material that doesn't really want to let those charged particles travel at all. So you probably agree with me, like rubber, glass, okay, oil is not very good, diamond, and the wood. So these are the stuff that doesn't really conduct electricity. So that's why usually you have like a rubber glove that you put on, and then you will be safe from get electrocute or something like that. Okay, so that's kind of sort of get that one. And then there could be something in between. Sometimes it can conduct, sometimes it might not. Then you get the semiconductor material. Okay, so it's something in between. But the good thing of something in between means you can manipulate the material to conduct electricity sometimes and not conduct electricity sometimes. So when you have some sort of like, hey, decision making like this, you can say, hey, yes, go, no, don't go, yes, no, yes, no, yes, no. Then you can use this to be like a logic material, the material that can do some logic, yes or no, yes or no. And then that lead you to, of course, the CPU and all this stuff. All right. And then you start building the transistor, and then you can control to, you know, start to do some logic and stuff in there. All right. So that's the semiconductor technology. And most of the stuff that you do is a silicon, of course. That's the one that has the semiconducting property built into it. Okay, sounds good. All right. I hope it works. All right. Next, this is the real stuff that we're going to do. I think maybe I talked too much this morning. Well, this is almost half an hour. Okay. This is the thing. How can we calculate that force, the electric force that we were talking about? And I think I wouldn't say easier way, but I think the way that I can introduce this to you is sort of like do it all in one. Most of the textbook will start from electric force, and then later they will go back to the electric field. Okay, but what I'm going to do in this lecture is I'm going to do it together in the sense that I'm going to start from the electric field. And it seems to me then eventually, once you understand what the field is, then you can get the force automatically. Okay. All right. I hope, just get along with me for now. Okay. The point that I think by introduce to you the field first seems to me is quite natural because you have already experienced that. And what I'm going to show you is this. All right, I'm going to grab something that's sort of easily drops and doesn't break things. Here we go. I have like a mass here. Okay. And everyone knows if I let it go, it's going to drop. Right? I have a mass here. I let it go, it's going to drop. At the position that I'm at the top over here, everyone knows there is a gravitational field. You guys with me, right? Okay. So the only thing that I'm doing is I'm just placing a mass there, and this mass experiencing the downward force because around here, actually it's everywhere, has the gravitational field pulling down all the time. Is that correct? So it means I can place it anywhere I like. And once I let it go, then there will be a downward force pulling this mass down. It seems to get stuck on me. Okay, yeah, there we go. All right. So that means already in this blank space in front of me, there is already a field pointing down, waiting for me to place an object in the field. And once this object is in the field, this object will experience the force. And because right now the field is pointing downward, once they place a mass in here, it will experience a downward force. Okay, let's do it one more time. Okay, I have a field that is pointing down. So let me sort of draw this. That's the field pointing down. I place a mass there. That's the M. What you do was, what you're going to do, or what you did before was you're drawing the weight, the W, right? And you say it's an mg, is that correct? All the mass has the weight m times g. Now you can understand why I'm trying to get you to the field. What will be the field that we're talking about? Is this g right here. That's it. So actually you have already used the concepts of field in the gravitational field. So what I'm talking about, space around me is already having the downward field from the gravity, gravitational field pointing down. Once I place the mass there, that mass will experience the downward force. Okay? Now, let's do it one more time. Let's imagine that this is not the gravitational field anymore, but it's some field. Some field. And it turns out this field interact with the charge. So I place a charge here. Let me call it Q, the amount of charge on that particle. It should do the same thing. It should experience the force due to the field. If I characterize the field by, let's say, letter E, then I should be able to say, hey, Ajahn, the force that acting on this charge should be just the same as what you did before with the mass times the field. But because right now the field is interacting with the charge, so I can do the force to be Q times E. You guys with me? Yes? And that's it. That's done. It's not done yet, but that's what it gives you, the relationship between the field and the force. Just like you get the weight from the gravitational field due to its mass. Is that good? I don't know. Any sign? Okay. So the only task that I need to get to calculate is, if I know how to calculate the E, that's now we're going to name this E electric field. Then all you need to get to the force is just multiply by the charge in that field, and you're done. You get the force. So that's why I will start our lecture with how to calculate electric field. If you know how to calculate the electric field, you will automatically know how to calculate electric force. And this business of force and field will be done all in one. You don't need to learn it twice. Well, 2 times, 2 topics. They are pretty much the same topic. Yeah, sounds reasonable? Okay. So what I'm trying to say is, what we are going to learn first is trying to learn how to calculate the electric field. Once you get to know how to calculate the electric field, there's no need to talk about the force too much, because all you need to do is just place the charge in the field and multiply the charge with the field to get the force. Okay. All right. I hope you see my logic of, get into this business here by now how to calculate the electric field. Okay. So by looking at this, now you understand the relationship between the field and the force. We can come back to this later. Okay. Once we learn how to calculate electric field properly. But now it's simply linked between the field and the force by the charge that we're talking about. Okay, sounds good. All right, so I make this slide looks pretty bad. All right. All right, but that's what I'm trying to get to. We can come back to this as a conclusion once we're done with the how to calculate the electric field. Okay, here we go. So to be able to visualize the field, because as you can see around me, there is no gravitational field that's visible to you or visible to any of us. So that means there must be a way that we can visualize the gravitational field. And the way that I already did was just using the arrow pointing downward, saying that, hey, there is some downward field pointing down right now. So we're going to do the same thing with the electric field. There must be some sort of like a line that try to represent the direction of the field. Okay. However, because every time you see this downward field is generated by like a super giant Earth right now. So we are on the surface of the Earth, so we can see the electric field is pointing. I'm sorry, the gravitational field is pointing downward. However, if you shrink down the Earth into like a point mass, of course, the field is not going to be like a single direction pointing down anymore. You see what I'm saying, right? So that's what I'm trying to get you to this. If the earth is shrunk down to like a tiny mass, or think the other way, if you go out into the space and sort of move so far away from the earth might look just like this small, just like a ball and stuff like that. You can tell that the gravity will pull towards the earth. So these lines, these orange arrows and the line with the arrows, that is representing the gravitational field. Is that correct? You guys with me? Okay. So this is going to be the same thing with the charge. So every time you have a charged particle, there must be the line representing the field. So we're going to call these electric field lines, just like gravitational field, same thing. But the only complication that I have to add on top of the gravitational field is you have now two choices of the charge. You have negatively charged particle and positively charged particle. While in the case of the gravity, you only have the attractive force. You never have a repulsive force before. Okay? So this is the stuff that we have to add on top is if you have a positive charge, now the electric field will actually point away from the positive charge. Okay? So now you have two cases. The positive charge will generate fields around it pointing away from the charge. If you have a negative charge, then the field will point towards it. Okay, cool. Okay, all right. However, once again, these are just visualization. Okay, in reality, of course, there will be no lines, but this helps. This helps to say, hey, if I am standing right here, okay, you guys come along with me here. If at this red dot, I am bringing Q naught chart. Okay, this is my chart, Q naught. And if this is a positive charge, what will be the force that this charge is experiencing? So, Odan, if you want to get to the force, all you need to calculate is, okay, come with me here. All I need to know is I can just get rid of this charge for a while and just calculate what is the electric field at this point. You guys with me? Okay. And because right now you are standing on the field that point towards the particle, so the direction of the field will be pointing towards the negative charge. Once you calculate this E, then I can go back and answer the question of what is happening to positive charge, Q naught, that I'm placing there. The answer is the force here will be Q naught times E. And I just put the vector there. And that is done. This is an overview of what we're going to do today. And that's pretty much it in terms of the in the nutshell. This is what you're going to do. Okay, come again, one more time. If I am standing right here on the left, and I want to calculate force later, acting on a charge, whatever. So what you need to calculate is what is the electric field at that point. And because you are on the electric field line that pointing outward, so at this point, all you need to calculate first is what is the electric field right here. With me? And later on, if you want to place a charge there, I could place like positive Q naught one more time right here. Then I can say the force acting on that will be just the charge times the field. Same thing. Okay, I hope you see the whole process. Get to the field first. Once you get to the field, then you can calculate force by asking, hey, what kind of charge you want to place there? And just multiply by the field, you get the force. Okay. Last thing, there is a nice thing about writing this equation in a vector format. Okay, let me ask you another question. What if you place a negative charge in there? What will happen? Here we go. Let's give it a shot. If I place a negative charge, okay, first, if I want to place a negative charge right here at the orange dots, first step, you say, Adan, let's calculate the electric field here first. The electric field will point outwards. Okay, everyone with me? Okay, because you are someplace around the positive charge particle, so electric field pointing away from it. And then you're going to place a negative charge there. Let me call it negative Q prime. Let's sum whatever numbers of the charge. What will be the force acting on that Q prime charge? You say about Ajan, force will be charge times the field. But because the charge is negative, do you notice something here? This equation is a vector equation. So it means whatever the electric field is pointing to, the force will point opposite to the field because of the negative sign. With me? Because right now the electric field pointing outward. So that means in this case, the force acting on the negative Q prime will point inward. That is the force. And that's perfect because look at this one. You have positive charge at the center. You place a negative charge particle nearby. At the end, the force is actually pulled toward the positive. That's why we say that in conclusion, this charge actually attract to the positive charge. They attract each other, of course, but let's assume that if the positive charge is fixed at the center, so the negative Q prime charge will get pulled toward the positive charge. And that's the attractive force between opposite sign charges. Sounds good? Okay. All right. So I hope, well, you see what can be done once we know what the electric field is. Everything is pretty much set for the force. So your task is how to calculate electric field at whatever point. And the how can I say, the basic of getting things started is understanding that around the positive charge, electric field pointing outward. Around negative charge, electric field point towards it. That's the starting point. Okay, now we have the last stuff that we want to add to it is the magnitude of the field. Now we get the direction down. Now we have to get to the magnitude. And the magnitude of the charge depends on this formula right here. Okay, almost done. This formula right here, actually, I already written down right here. That's the same equation. And this is the equation we're going to use back and forth all the time. This is how to calculate the electric field from the charge that originating it. Okay. Even though it looks confusing, but it's not too bad because, okay, first of all, there is a constant in it. Okay. So you can call this like a Coulomb constant, but we're going to name them properly later. The charge that's generating the field, okay, and that is the one that's generating the field. And all you need to calculate is just measure the distance from the charge and you square it. So it turns out is an inverse square law. Just like what you saw before in F equal to G m over r squared. If you sort of memorizing the gravitational force before, it's an inverse square law. It's pretty much the same kind. So what you have over here is the further away from the charge that you try to calculate the field, the magnitude of the field will get smaller and smaller, but it's smaller as the 1 over r squared. So it's go down quite quickly. Okay, sounds pretty good. So that means further away from it, the strength of the field will getting weaker and weaker and weaker, which is sort of like agreeable because if you go further away from the surface of the earth, you will feel less and less gravitational field. So that means the closer to you to the center of the earth, the stronger. Well, the earth is big. Okay, let's say from the surface of the earth. So when you are on the surface of the earth, you get gravitational field like 9.8. Yeah, that's your G. But then you further away from the surface of the earth, then your gravitational field is getting smaller and smaller. And then you go far away, and if you far enough, then you can say the influence from the earth gravitational field is going to go to zero. So same thing over here is 1 over r squared. So in the limit of r is so big, the field will just disappear. All right. So with these two sort of ready, and then we can just start sort of attacking problems, and then you will see how to calculate this. First, direction. Second, magnitude. Once you get these two, you get to the vector that representing the electric field. Then you're almost done already. Okay, guys? I know, okay,วันนี้ดูเครียดหมด All right. But this is the first time that I spent like 30-40 minutes explaining this couple of slides here, because in the past it seems like, well, I just talk about like 5-10 minutes and then dive into this field right away, and it turns out many of you seem to confuse because we are dealing with vectors that invisible. Actually, you cannot see it. All right, so let's start with this simple sort of like question, right? It's sort of like not quantitative like the one that we're going to really do it, but let's testing our basic understanding of how the electric field is behaving around charges. So start with this. You guys do all right so far? It's just hello, okay, yes, just like okay, no response. Like type 1 if you okay, 0 if you feeling not so well. All right. Oh, it's the 1. All right, thank you. All right, good. Okay, so let's start with this. It's gonna be quite fun today. All right, it's tough business a little bit. All right, it's a vector stuff. Okay, so in the figure, two particles of charge Q are arranged symmetrically about the y-axis. Okay, so the figure is nice and clean. Each produces an electric field at the point P. A. Are the magnitudes of the fields at P equal? What do you think, guys? Yes or no? Yeah, so the way that you think about this is first, directions, right? If you think about the directions, you just gonna have to sort of like, draw this line by having the charge at the center. Okay. Second of all, the directions, it's going to be toward the charge when it's negative. So it means that for the left side charge, the field will point towards it. You guys with me? Okay, that's a negative Q. So the field point towards the negative charge. Same thing on the right. There will be a field point towards it. Okay, sounds good. Second is what the magnitude. The magnitude depends on how far away from the charge originating the field. Look at the left. The distance from the charge to the point of interest, let me call it R. But from the symmetry, same thing happens on the right side as well. Yes. Very good. So from the expression of the formula, we know that actually at point P, I can write it like this. Electric field at point P from the left. Let's start from the left. will be just the magnitude. K, a constant. The charge generating it, that's a Q, divided by R squared. That is the magnitude of it. You guys with me? Okay. And now when you look on the right, it seems to look the same. Electric field at point P from the right charge, it's going to be K, the charge generating it, divided by R squared. Because the R are the same, so yeah, the magnitudes are the same. Yes. Okay. Now, second, each electric field directed towards or away from the charge producing it, of course, is going to be toward, because these two charges are negatively charged. Part C is the magnitude of the net electric field at point P equal to the sum of the E. Is that right? Now, this question asking you if I quantify this to be E. Yeah, that's what it says. If the is the magnitude of the net field equal to the magnitude E of the two vectors. So that means each electric field vector, let's name it E. And now we know these two having the same magnitude. They're both E. This is E. This is E. Is the sum of the two equal to 2E? Well, of course, no. That's not possible. Why? Because we have to do the vector sum. You guys with me, yeah? Just like when you do summation of two forces. You cannot just add this to E to get 2E. No. So what do? You do the components. You split this, split that into a vertical and horizontal. Do the same thing with the right side, E, that. You do that. So what you're going to get is you're going to get electric field in the Y direction, electric field in the X direction for both of these two electric field. The red and the orange. There we go. The orange, yeah? All right. So part D, do their X components add or cancel? Of course, X components seem to point in the opposite direction, so definitely they're going to cancel. And do their Y components add or cancel? They're pointing in the same direction they're supposed to be added. And what should be the net field direction, you guys? Of course, you say at point P, eventually you're going to get, this is going to be the net electric field. It's going to point downward because the horizontal components already canceled each other. So what is the net field direction? It's downward. Looks good. Yeah. Okay, just start to get the feeling of what we are about to do here. First, try to get to the electric field direction. Okay, consider the type of the charge. If it's positive, the field is pointing away from the charge. If it's negative, the field pointing towards the charge that originating the field. Second, measure the distance from the charge, try to originate the field, and that we name the distance R. And then once you know the R, you use the KQ over R squared to determine the magnitude of the field. Third, if you have a bunch of these electric field vector, you have to do the vector summation. Oh, okay, I already wrote it here. It has to be sum using the vector summation. Okay, cool. It's not cool. It's just like that's a process that you have to go through. Wow. All right. Okay, slowly sort of, if this is good, then we're just gonna dig deeper. All right, it's gonna sort of like, it's gonna be a ride here. Okay, try again, guys. Okay, this is a good, not so easy exercise, but I love to have this one as a starting example because it's sort of trigger your sort of like imagination or whatever you're thinking in the electric field stuff very, very nicely. It seems to me that way. Give it a shot. From the figure, determine the point, of course, other than infinity, at which the electric field is zero. Because if you go so far away, infinitely far, then of course you're going to get zero field. But no. Let's find the point around here that give you zero field. All right, you guys try this. I want you all to try this one. I think this is a very good sort of like, exercise to it needs everything pretty much. You need magnitude, you need directions, you need to figure out the position that eventually those vectors have to do summation and eventually cancel themselves out. So this is all in one. Magnitude, directions, vector summation, all in here. Okay, guys, give it a shot. I'll give you like 2-minute head starts. They want the problems want you to determine the point at which the electric field is zero. Wow. It must be somewhere. Okay, it has to be. All right, I'll give you 2 minutes. I don't know, you guys. I don't just, do the solution now. Don't waste time waiting for me. I'm just gonna wait for you, and then you wait for me, and then I'm gonna wait for you, and you wait for me. Okay. All right. First of all, where should it be? Roughly. We should sort of give like a rough estimates first. Like, where should it be? First thing first, because we know to be able to get to the zero field, the vector summation must be perfectly canceled between those two vectors. Because right now we have two charges. You're going to generate two electric fields. And to be able to have a zero field at the end, those two electric fields need to be canceled each other out perfectly, right? That's the key. And that gives you something that's to be clear. The point that electric field will be equal to zero has to be on the line connecting between these two charges. Why? Because if you pick a point, let me call point M, that is not on the line that connecting between these two charges, electric field from the left hand side charges, okay, let me use a light blue to leave like that one. So what you are going to get is this. If you pick a point that is not on the line connecting between these two charges, it means the vector, electric field vectors that generated by these two charges will not going to line up. Whenever you need perfect cancellation, it means one has to point opposite to the other. Is that right? That's to get a perfect cancellation. You want to cancel them. These two at least must be on the same line of sight. You have to think, okay, you are on the same line here. So you're going to get perfect cancellation. If you have some angle between them, there's no way that you're going to get cancellation. Like here, if I pick a point M, look at this one, the blue charge is a negative charge. So electric field point towards it. Okay. The orange charge is positive charge, electric field point away from it. Okay. However, they are not going to line up because these two vectors going to make some angle no matter what, no matter where you pick a point that is not on the line connecting between the two. Okay. So at least the first conclusion or the first step that you have to sort of at least, okay, if I want to guess the position of zero field, it must be on this line connecting between these two charges somewhere on here. Okay, it must be, let's say that's on the x-axis. Let's say if I draw a line and I call a horizontal axis here to be x-axis, it must be on this horizontal line right here. Okay, you guys follow? Yeah, first of all. Second step, now because you say, okay, it must be on this horizontal x-axis line here, Now you have three choices. It could be somewhere to the left, somewhere in between, or somewhere to the right. Yeah. Okay. So this is what could happen is it might be somewhere around here, the green area, or it could be somewhere in the middle, or it could be somewhere on the right. There you go. There are three regions of interest. Okay, let's start from the right. So let's say about, hey, Ajahn, from the look of this one, it could be somewhere around here. Let me pick a point once again. Let me call this point N. Okay, so at point N, now you can see that, here we go, the electric field due to the negative 2.5 microcoulomb charge will be pointing to the left. You guys with me? Oh, here we go. Yeah, you guys with me? Yeah? It's the negative 2.5. Electric field point towards it. At the same time, the 6 microcoulomb is positive charge. It will generate the field point to the right, the orange one. Okay. However, look at the distance. The blue one is far away. The orange one is actually pretty close. Okay. So what I'm saying over here is the K, Q over R squared for this one, and the K, Q over R squared for this one, I color coded here. You're gonna see that because the distance for the orange one is small, so the electric field will be big. For the blue, the distance is far away, so the field will be weak. So what you're gonna see that on the right side of this area, the blue arrow, the electric field from the blue charge, will always be smaller than the electric field from the orange charge. You guys with me? Okay. Or what I'm saying is the magnitude of the field generated by the orange charge will always be stronger than the electric field that you're going to get from the blue charge when you are on the right side of this one. So you're never going to get cancellation because the blue always lose. The orange is always bigger, is always going to win. So the net electric field will always be point to the right all the time. Okay, try again. If you move a little bit closer, let's look at the middle region here. Let me pick another point. Let me call point O. Okay. Now, the electric field from the blue will point to the left. Okay, point to the left. Electric field from the orange also point to the left. You guys with me? Okay, the blue is negative. Electric field point towards it. The orange is positive. Electric field point away from it. And it turns out they're going to point in the same direction. So this is not good. They are not going to cancel. So it's impossible for you to find a point where you get zero field somewhere in between these two charges. Now, you are left with just the last choice. It's probably somewhere around here. Is it possible? When you look at this one, you say, okay, electric field from the blue charge will point towards it because it's negative. And the electric field from the orange charge will point away from it. It's going to point to the left. And because the distance from the blue is small and the distance from the orange is big, it might just perfectly compensate for the smaller charge of the blue. You have a smaller charge, but you compensate by, okay, I'm going to stay a little bit closer. The orange one is larger charge. However, okay, I'm going to stay away a little bit further from you. So you might be able to find a point where you get the balance between these two and then generate the electric field of the same magnitude. and eventually they're gonna perfectly cancel because they are pointing in the opposite direction. That's possible. Okay, so this looks promising. So let's name that distance x away from the blue. Okay, so let's start from this one. So what I'm saying is I'm going to try to figure out the magnitude of the blue electric field. That eventually they're going to be equal to the magnitude of the orange electric field. I use color coded here, okay? All right. Okay. So the magnitude of the blue electric field is going to be K. The charge from the blue, 2.5 microcoulomb, divided by the distance square, which is x perfectly. This is x. Point P is x away from the blue charge. It's going to be x squared. And this is supposed to be equal to the electric field from the orange charge. It's going to be K. The distance now is going to be x plus 1. You guys with me? The total distance over here is x plus 1. So that's good. The charge is 6 microcoulomb, and then divided by 1 plus x squared. And that's it. That's it in the sense that now K cancel. You don't even have to substitute the K in there. The Coulomb or microcoulomb, you don't even have to do units conversion as long as you use the same microcoulomb units on both sides. Now solve for x and you're done. Is this a good starting example? I don't know. All right. If you still confused a little bit about this exercise, that's okay. Because there's so many things on this one. When I say many things, it's pretty much everything. Magnitude, directions, and vector summations is all in here that you need. Okay, so I think this is a good exercise that you might want to come back again when you sort of have some more experience with electric field calculation. I think this is a good review exercise all the time. All right, I don't know, is it so far so good so far? So far so good so far, I hope. All right. Woo. Okay. Okay, not too bad. Not too bad. All right, get going. Next. All right, so we'll do a bunch of this one. A bunch, I mean, yeah. I think the best way to try this one is just keep trying, because in terms of the formula or in terms of the the principles and everything, that's pretty much it. There's only one principle: is the electric field has some formula. That's only single formula, but the complications comes in when you have to do the vector sum of those fields. I think that's the difficulties of this subject right here, this topic right here. Okay, try again. Okay, everyone try this. You have three equal positive charges Q that are at the corners of an equilateral triangle having the side A as shown. What are the magnitude and direction of the electric field at point P due to the two charges at the base? Okay, want to try this? Everyone should try this. Okay, let's get things started here. So I think this is another, so it's intentional to have three charges here, but asking to figure out just electric field at the top of the triangle. The reason for this is because they want to figure out the field at point P. So what I'm saying is you actually don't care. Okay, let me do this. You actually don't care that there is a charge here at point P. You guys with me? Because you want to calculate the electric field at point P due to the charges at the base. So it doesn't matter there is a charge at point P or not. You don't care. You just want to know, is there any fields at point P or not from the other two charges. Okay, clear? Okay. So what I'm going to try to do is this. First, start from the left. it's a positive charge. You look at this from point P. Because it's positive, electric field should point away from the charge originating the field. Okay. What is the magnitude of this? Let me call E left then. You say it's going to be K, charge over distance square. With me, guys? Okay, very good. Now you get the magnitude and direction done for the left hand charge. Do the same thing for the right. You look at the charge from point P. You see there is a positive charge there. So that is the electric field point away from that positive charge on the right. Let me call this E on the right, E sub R. And because it's at the distance A away from the charge, the magnitude of it is going to be K, the charge generating the field, divided by the distance square. Okay, why do I have to write this one diagonally? Sorry, guys. Okay, let me write nicely here. Okay, E on the left. That's just K Q over A squared. Okay, very good. Okay. So now what you need is you want to find the net electric field at point P. So do it. So what I'm going to do is, once again, you split this into two components, vertical, horizontal. Do the same thing for the right. Okay? And now you can see that the horizontal components will cancel. So the net electric field will point upward due to the vertical components of these two electric fields. Okay, all right, very good. And from the geometry, of course, you know that this is 60. It's an equilateral triangle. Okay, so that means you know this is going to be 30, and this is going to be 30, half of the 60. Okay, so conclusion is the sigma E, the net electric field, is going to be E on the right cosine 30. Okay, you guys with me? I want just the vertical components on the left. This is E sub R cosine 30. And this is going to be E sub L cosine 30. Okay, there's a vertical component of these two vectors. So I'm just going to add that with E sub L cosine 30. Here you go. However, we know these two terms are the same. So the net is going to be 2 times K times Q over A squared cosine 30. Or you can write cosine 30 to be root 3 over 2. Up to you. That's fine. Okay, and you can say it's upward direction. Let me put the arrows here. It's point up. It's pointing up. Okay, cancel. Okay, and for those of you that are familiar with the vector notation, you might just say, well, Ajahn, I can do like a sort of cool notation that I learned before, KQ over A squared, and then you can say it's J hat. That's if you sort of familiar with this kind of thing, that's fine, that's nice. So you can say it's pointing in the positive Y direction if your axis is standard XY. Okay, but for those of you that don't want to deal with this at this point, that's okay. Just saying that it's say pointing up, that's good enough. Or just write an arrow here. I think this is good. All right. And just to, even though we are in the sort of topics of electric fields, but I think I'm just going to just flash forward and ask you about, hey guys, can you tell me what is the force acting on the charge at the top of the triangle? Will you be able to answer that? That means if I bring back that charge the charge that I erased. I'm just going to bring it back, place it here. That's a Q. What will be the charge acting on the charge Q at the top of the triangle? You probably say, Dan, that's easy. The force is just the charge times the field. With me, guys? And that's it. You know that the force acting on this Q charge will also point upward as well, because the E is pointing upward. See, this is how easy it is to get to the force. Once you know the field, you just multiply by the charge that you place at the position of that field. You get the force. So it seems to me, once you know how to calculate the electric field, the force is no issue. Cool? I know you guys kind of quiet, but I hope everything is going well at this point. Okay, keep going, yeah? Try again. All right, you guys try this. So think of today as like a workshop. There are so many examples and exercises that I want you and me just gonna go through these together. I think it seems like that's the easiest way to get through this one. That's why there's so many exercises in this handout. Otherwise, then, well, it's gonna get a little bit confusing. Okay, the figure shows two charged particles on an x-axis. Okay, very good. Now one negative, one positive. All right, that's good. The magnitude of the charges are given. The position, x position is given. What are the magnitude and direction of the net electric field produced at the point P at y equal to 4 meter? Okay, very good. I think it's missing equal sign there. Okay. So what it is this side is 4, this side is 3, something like this. Okay, so it's good. It's a 3 to 4 to 5 right triangle. That's we love. Okay, now it's actually very close to this exercise, almost the same. But now we're gonna try some things different in terms of you have opposite charges. So let's look at this. Once again, you are at the point P. You're looking at the charge negative Q on the left. You see that it should generate electric field towards that. See, it's pointing towards the charge generating the field. Okay, so let me name this E negative. What is the magnitude? It's the K times the Q divided by, of course, it's 3, 4. This must be 5. So it's going to be 5 squared. You guys with me? So now you get that left side charge electric field done. Now let's move on to the right. You are at point P. You're looking at the positive charge Q on the right. It's positive charge, so it's going to generate electric field pointing away from it. Okay. But then you can calculate. Let me name this electric field from the positive charge. Let me call E sub plus. And that will be K times the magnitude of the charge times, once again, it's still 3, 4, 5. So it's going to be 5 squared. So actually it's almost the same thing. Except now, of course, once you want to add these two together, the component that turns out to be cancel, it's now the vertical components now. Because these two vectors having the same magnitude. So once you break into two components, the vertical component cancel. So you will be left with just the horizontal components, twice, 2 of them. Okay, looks good. And now you can define your theta, whatever you like. All right, let me use this. Oh, up to you now. If you want to use, this is to be theta, and that would be your theta right there. Okay, so if you name that, so what you have over here is going to be the net electric field will be equal to the horizontal component. Let's do the horizontal component from the green. The E positive is going to be E positive sine theta. You guys with me? Okay, let me write it in here. That's a E positive sine theta. And you're going to have another one, E negative. Let me use absolute, sorry. Okay, there you go. Here we go. All right. So you get two of the horizontal components that you want to add together. So you say, okay, oops, sorry. That will be E negative sine theta. Okay, and now everything is good because its magnitude are the same. So it's going to be twice of the K times the Q over 5 squared. Sine theta is the opposite over hypotenuse, so it's going to be 3 over 5. And now at the end, you can substitute all the numbers that you want. K is given in the exam, so you don't even have to memorize it. It's 9 times 10 to the 9. The Q that's given here, that's 3.2 times 10 to the negative 19. Let me omit all the units here, because I know at the end you're going to get Newton at the end. So that will be Newton right there. Oh, sorry. It's an electric field. So actually it's a Newton per Coulomb. Okay. All right. So once we arrive at these problems, we have done quite a few. You notice something here? That every time that I try to calculate the magnitude of the field using KQ over R squared, right? I don't substitute the negative sign into this expression anymore. Okay, let me emphasize what I'm talking about here. See, when I try to calculate using this formula, I always just put the magnitude of the charge. See, even though this blue charge is a negative 2.5, but I just only put 2.5 here. So I don't care is a positive or negative charge is being considered. I only need the magnitude of the charge in the formula of magnitude of the electric field calculation. The reason is, okay, let me show you what I mean here. See, when I have this, actually I don't care this is positive or negative. I'm just going to use Q in my expression here. Even though one side is negative, the other side is positive. But when I plug it in here, I just only use the magnitude, even though one is positive and one is negative. The reason that I don't need to put negative sign into this expression anymore, because the negative for the vector quantity represent the direction. You guys see what I'm saying here? Yeah? So that's why once I know which direction the electric field should point to, the rest of my task is just to figure out the magnitude, which there's no more negative sign in it. Okay, magnitude is always positive. Okay, so that's why once you already pinpoint the direction of the electric field, when you turn your attention to magnitude calculation, all you need to plug in is just the magnitude of the charge. You don't have to worry about the positive or negative anymore, because you have already taken care of in the directions, yeah, of that field. Positive away, negative towards. Okay, all right. Okay, one more, and then I think then I'll draw some conclusion, and then we can take a break. Sounds good? I don't know, is this heavy or light? I don't know. You guys can give me some feedback here. All right, seems like a couple people left already. All right, but this is pretty much, it's, well, I said in this course, this is the part that is pretty hard. I think this is, at almost the peak of the difficulty of the course, I think. All right. But next week maybe a little bit softer, I hope. All right, this one is the toughest one, because so many things going on. All right, you guys still okay? All right, okay, let's do one more just to test your understanding, and then we're gonna wrap up a little bit in terms of what it means by those electric field properties, and then okay, we can get some break here. Okay, try this one, guys. Okay, this one just give you some twist in the sense that now I'm not gonna stick with the horizontal vertical anymore. It's just free floating set of charges, and then just, hey, what is the electric field at point P? Just sort of like do it. Okay. The problems that shows up in the exam, I think, is about this level here. I mean, it's about the same. It's the level that we have been doing. This is about here. So don't worry that things are gonna get more complicated than this. I don't think it's gonna get anything further away from what we are doing here. Okay, in the figure, you have 4 charges. All right, Q1, Q2, Q3, Q4. The magnitude of those Q's are given. Positive, negative, that's fine. I can mark the sign just to make sort of like some reference to it. Okay. Only Q4 is negative. Now the distance Z are all the same. You want to figure out the net electric field at point P. So if we think sort of in just like all the steps that we have been doing, let's start from the Q1. You at point P, the Q1 and point P, yeah, you are standing at point P, looking at the Q1. Q1 is positive, so it's going to generate the electric field point toward the right. I mean, it's not right, it's diagonally down a little bit. Is the green arrow there. Okay, now you're standing at point P, looking at Q2. Okay, because Q2 is also positive, so it's going to generate electric field point away from it. So the electric field from Q2 is pointing away from it. So let me name this one E sub 2 and name the first one E sub 1. Yeah. Number 3, electric field from Q3 once again is positively charged. So the electric field from Q3 is going to point away from it. Let me name this E3. Okay. And Q4, the Q4 is negatively charged. So I should get the electric field point towards it. Let me name this E4. All right, and of course, all of these should be vector, so I just put an arrow on top. There you go. Okay, you guys with me? But one thing about this one is, if you notice electric field number 1 and electric field number 2, you see something here? Because the Q1 and Q2 are having the same magnitude, and point P are at the same distance away from these Q1 and Q2 charges, so that means the magnitude of E1 and E2 must be the same as well. And because they are pointing in the opposite direction, so it turns out actually these two will definitely cancel each other. Yes. So the only business left for you to calculate is just what is the net summation between E3 and E4. Yes. All right, very good. So actually this is not too bad. Even though it's sort of free floating, you don't have horizontal, vertical, but it seems like the only thing left for you to calculate is just subtraction between these two E3 and E4 magnitude. Okay, that's not too bad. So let's calculate the magnitude of the E3 electric field first. Okay, it's going to be the K, the charge Q3, over the distance, which is D square. That will be the E3 magnitude. E4 magnitude is going to be K, Q4, over, now it's going to be 2D, twice as long, square. Okay, and now this is almost done. All you need to do is just sort of stick with one directions and go with it. So I can say, hey, let's call this direction to be the positive directions. So you know the end result. If once you take these two numbers and subtract, if the net result is positive, it means the net electric field point towards the Q4, Q3 directions. Or once you calculate this subtraction and then you get the negative numbers, it means it's going to point away. So it means the net electric field in the same direction as the E3. Yeah, make sense? Okay, so let's do that. So the net electric field is going to be the E4 subtract the E3, because E4 pointing along the positive direction and E3 is pointing opposite. So I have a negative sign in front of the E3. All right, and now K is there. Q4 is 12E. See, I don't need to take the negative sign into this anymore. Over 4D squared. And then I subtract with the K, Q3, which is 3E, over D squared. Okay, and this is a good thing of not doing the numerical calculation right away, because you can notice this. Whoa, nice. It's just accidentally to be the same size, same magnitude. So the net electric field at point P is 0. Okay. Oh, this is a good exercise, yeah? Right. You don't have to do the sort of calculator punching or anything at all. It just perfectly cancel. Is my math right? Yeah, I think so. 3KE. Okay, good. All right, but I hope by looking at this sort of 3-4 exercises here, so you can see how to determine the direction of the electric field from a charge, how to calculate the magnitude from a charge, and then eventually, when you have a system of charges, you have to do the vector summation. So you have seen how to sum those vectors. But vector summation is vector summation. So it's just the same thing as what you have done with the force summation, for example, yeah, or any vector that you have to sum. It's just a vector summation. So you do component summation, you do whatever you have done with the vectors. You just do it here. Okay, pretty much that's wrap up how to calculate the electric field. So there is a little bit of the properties of the electric field that you should know. However, I think by saying that now, it's going to add on top of things that might be confusing already at this point. So don't worry about this much, because I think it will come naturally later. That when you do calculation about this more and more, then you start to understand why the property of the electric fields need to be so. However, there are two things that I want you to get at this point. All right. First, look on the right. I don't know you get a sense of this one or not. If you have the electric field lines that look like this, okay? So, can you tell that the position at point P or point R, which position having the stronger electric field? Can you tell? It looks to be point P. Is that sort of resonate with your thinking? Yes. Because the lines are pretty dense around point P that reflect that it's sort of like something sort of intense there. So it seems like the strength of the electric field point P seems to be stronger. At point R, the lines are further apart. It's kind of weak. So electric field at point R seems to be weaker. Yeah, does that make sense? Because, I mean, this one may be a little bit sort of confusing to you, but here, let me come back to just this starting point. You can see that when you are closer to the charge, see, you see that the density of the line seems to be quite dense in comparison to when you are further away. The lines seem to be further apart. Okay, so that's sort of like a good sort of visualization to say that every time you have like a very dense electric field lines, that will be the region of high or strong electric field. And when you have electric field lines that further apart, sparse, everything is just further away, electric field strength is gonna be low. Okay, okay. All right, like this one right here. See? So this seems like on the surface area A, the electric field seems to be stronger because it seems like very dense. And then when you move away, further away in the direction of the field, seems like the electric field line is getting separated. So it seems like the electric field strength is getting lower and lower. Okay, okay. Try again over here. If you see electric field lines looks like this, you know that this area will be very strong in electric field strength. And when you go further away out here, it seems like it's going to be quite weak. Something like that. Okay, so at least that give you some relationship between the density of lines and the electric field strength. The higher the density, the stronger the fields. Okay, the second one is, this is a thing that you shouldn't be able to see at all because those lines shouldn't cross. Okay, because if there is a crossing, then you have no clue which direction of the electric field should be. Okay, all right. So that's why every time that you look at the electric field lines, so it's a good thing is like a visualization just saying that, okay, once I have the line, I can tell right away what should be the electric field at a point. And the electric field will be just in the direction that's tangent to the electric field line. So that's kind of easy. Okay, so I hope, well, I say I don't want to explain it, but eventually I explain them all. It's like this. When you have an electric field lines of a system of charges, then you know you can, hey, what is the field here? It's going to be tangential to those everywhere, pretty much. Okay, all right, it's just going to be something like this. So once you get the lines, you get to see what's supposed to be in terms of directions and magnitude. Directions, tangential to the lines. Magnitude, you have to look at the density of the lines. Okay. All right. Woo. All right. All right, and this wrap up what we're talking this morning right here. Once we get to the E, we will be able to shoot for the F very easily. All right, sounds good. I think this is a good point to break. I guess you guys seems pretty quiet today. I mean, I don't know. It's quiet because everyone's mute their microphone, of course. You guys still okay? I just send me some signal that you guys still alive and well, and having some snacks and breakfast along with the lecture. Yeah. All right, I think I'm okay. Thank you. All right. Oh, that's still number one. Oh, that was okay. An hour ago. Okay, so let's. Yeah, I know. Content is pretty hard. Okay, so don't worry about this. 0 now. Okay, so let's take a break here. When we come back, we'll have another chance of getting to this.